Hello, this is the next video in a playlist that I'm calling Correlation. And in this video we're going to look at the semi-partial correlation. This is actually part 2 of a two-part mini-series on semi-partial correlation. Now, as a reminder, the semi-partial correlation looks at the correlation between y and a variable, say z1, after removing the effects of the other p-1 variables from z1. And it turns out that after we regress z1 onto the other z variables, we look at that residual, and then we take the zero order correlation between y and the residual after regressing z1 onto the other predictor variables. And so correlation is covariance divided by the product of the standard deviation. And in part 1 we looked at this in a little more detail. In this video, I wanted to show the relationship between semi-partial correlation and type 1 sums of squares. And to me, it's an intriguing video, or intriguing result. Now, to do this, first of all, we're going to look at the multiple correlation coefficient, the squared. Now, in a video I called multiple correlation, we showed that the correlation between y and the fitted model with the p variables, that is multiple correlation. And it's the square root of this. So if we square the multiple correlation, then it gets rid of that radical sign. And that's what we want to do. Just makes it easier. So this was the formula that we derived in this video. Now what we want to do here is z, there's p variables. We want to isolate that first one, the z1. And we're doing that because of the partial correlation between y and z1 after controlling for the other z variables. We have to break it down into that fashion. So this covariance matrix, it ends up being a vector between y and the z's. It's the covariance between y and z1, and then the covariance between y and all the others. Predictors, or all z variables. So this is a vector, a 1 by p-1 vector, and then this covariance matrix, we're going to break it down into the variance of z1, and this is the covariance between z1 and all the others, and of course it's symmetric. This is the variance between the other predictors, not z1, so it's z sub minus 1, the inverse. And then here, this vector, we're isolating z1, and this is the remaining. Now, the divide by, we're just going to put on the end, and that's really to save paper in this video, instead of writing it under and wasting paper. So now, the inverse of this matrix, we're just going to call the result, whatever it is, A, B, C, D. So then when we take this vector times it, we get this. And then everything else comes down. Then we take this vector times this, and we get this result. Of course, divide by the variance of y. Now, I have a video called The Inverse of a Partitioned Matrix, where we give explicit formulas for A, C, B, and D. And that's this result. It's kind of messy, but it'll come to a point in a second. So A is this piece, C is actually this piece, right? Those two end pieces are here. B is in here. D is actually this piece and this piece divided by the variance of y. Now notice this doesn't have a divisor, and these four do. So we're going to combine those four. It actually factors into the product of these. So if you take this times this, that's this. And then this times that, and then this times that, and then that times that. You get this back. Now this piece here, I want to show you something that when we started, this was the multiple correlation coefficient. And so this is actually the same form, except for everything's exactly the same, but we've removed z1. So it's actually the square root of the multiple correlation between y and all the other predictor variables, z sub minus 1. And then this. So, and then the next subtlety is this numerator here. we have the covariance between y and z1, covariance between z1 and y. Those are the same. Now here, this is a number. This is a 1 by 1 matrix, which is a scalar. So this is a scalar. So we can take the transpose and it doesn't change it. But notice when you take the transpose, this becomes the first, over there, which is what this is. That's symmetric, stays the same. And then this piece, when you take the transpose, actually gets moved to the back. So this product's the same. So we can just square it. And that's what we do on this next page. So everything else just moves to the back. Then in another video, we show very explicitly that if you take the covariance of this quantity, you get this, the variance of y, and then the variance of this ends up being this piece here. R squared comes down. Well, this is the residual after regressing z1 onto z minus 1, all the other regressors. So that's the covariance between y and the residual, and this is the variance of y, the variance of the residual. Well, this is the definition of semi-partial correlation, or part correlation, same thing. And so if we take this, subtract it to the other side, we get the squared semi-partial correlation is equal to, the squared multiple correlation minus the squared multiple correlation. So, and this right here we use all the time. So in linear regression, we regress y on the p minus 1 variables, then we add one variable and then look at the coefficient of determination, and we hope that it significantly increases. That one variable we added is contributing above and beyond what the other variables are contributing. And that's a great definition of the semi-partial correlation coefficient, or at least the squared of it. The correlation between y and z1 after removing the effects of the other variables, z minus 1, is exactly interpreted as this. But this is the sum of squares regression over total, sum of squares regression over total. This is using all p variables. This is using p minus 1. Common denominator. So it's the difference of these sums of squares regression, and that's what we call the type 1 sums of squares. This is the notation we use. That's type 1 sum of squares. And I'm gonna pass you off to a video, multiple linear regression, type 1 sum of squares. So the semi-partial correlation, or at least the squared, is related or has a relationship with the type 1 sum of squares. And to me, that's kind of neat, and it really makes me think about how we interpret the partial f-tests in type 1 sums of squares. And it can really be thought of as that correlation, the semi-partial correlation. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.